Voltage drop in a circuit can be calculated using a formula. This formula multiplies the voltage by the resistance, current, and distance. The voltage represents the voltage at the source, in this case 480 volts. The resistance is the resistance of the wire per unit length, measured in ohms per foot. The current is the current flowing through the wire, measured in amps, and the distance is the length of the wire in feet. Power factor measures the relationship between real power, which is the actual power used by the load, and apparent power, which is the total power flowing through the circuit. A power factor of 1 indicates that all the power is being used by the load. A power factor of 0 indicates that all the power is being wasted in the circuit. In alternating current circuits, power factor is determined by the phase shift between the voltage and current waveforms. When the voltage and current waveforms are in phase, the power factor is 1. When the waveforms are out of phase, the power factor is less than 1. Power factor affects voltage drop because it affects the current flowing through the wire. A lower power factor means that more current is required to deliver the same amount of real power to the load. This increased current results in a higher voltage drop. In shorter run applications, the voltage drop is typically negligible, and the wire size is determined solely by the ampacity or current carrying capacity of the wire. However, in longer run applications, the voltage drop becomes more significant, and the power factor must be taken into account. A power factor of 0.8 indicates that the current flowing through the wire will be higher than if the power factor were 1. This higher current will result in a higher voltage drop, which is why the power factor must be factored into the voltage drop calculation. The National Electrical Code, or NEC, provides guidelines for voltage drop in branch circuits and feeders. While not mandatory, it's generally recommended to limit voltage drop to a maximum of 3% in branch circuits and 5% in feeders to ensure efficient operation of electrical equipment. Voltage drop calculations help determine the appropriate wire size to keep voltage drop within acceptable limits. Several factors influence the choice of wire size for a particular application. Firstly, ampacity is a crucial factor. The selected wire must be able to safely carry the calculated load current without overheating. NEC Table 310.16 provides ampacity ratings for various wire types and sizes. Secondly, voltage drop is another significant consideration, especially for long circuit runs. As previously discussed, excessive voltage drop can lead to inefficient operation and potential equipment malfunction. Thirdly, the type of insulation affects the wire's ampacity and suitability for different environments. Common insulation types include THHN, THW, and XHHW, each with different temperature ratings and moisture resistance. Fourthly, the installation method, such as conduit type and fill, impacts the wire's ability to dissipate heat and affects its ampacity. NEC tables provide adjustment factors for ampacity based on the number of conductors in a raceway or cable. Fifthly, environmental conditions such as ambient temperature and exposure to corrosive substances can affect the wire's long-term performance and require specific insulation or protection measures. When performing voltage drop calculations, it's essential to use accurate data and consider all relevant factors. Here's a step-by-step approach. Firstly, determine the load current. Calculate the current drawn by the load using the formula current equals power divided by voltage multiplied by the power factor. Secondly, determine the wire length. Measure the total length of the circuit, including both the supply and return conductors. Thirdly, determine the wire resistance. Obtain the resistance per unit length of the selected wire size from NEC Chapter 9, Table 8, or manufacturer's data. Fourthly, calculate the voltage drop. Use the voltage drop formula to calculate the voltage drop in the circuit. Fifthly, compare the calculated voltage drop to the allowable voltage drop. Ensure that the calculated voltage drop does not exceed the recommended limits. If the voltage drop is too high, increase the wire size and repeat the calculation. In addition to manual calculations, several online voltage drop calculators and software tools are available. These tools can simplify the process and provide more accurate results by considering factors such as temperature and conduit type. Power factor correction involves improving the power factor of an electrical system to reduce energy waste and improve efficiency. A low power factor can result in increased current flow, higher energy losses, and reduced system capacity. Power factor correction is typically achieved by installing capacitors in the electrical system. Capacitors store electrical energy and release it back into the circuit, which helps to offset the reactive power caused by inductive loads such as motors and transformers. By reducing the reactive power, capacitors improve the power factor and reduce the overall current flow in the system. Power factor correction offers several benefits. Firstly, it reduces energy costs. By improving the power factor, the amount of apparent power required to deliver the same amount of real power is reduced, resulting in lower energy bills. Secondly, it increases system capacity. Power factor correction can free up capacity in electrical systems, allowing for the addition of more loads without overloading the system. Thirdly, it improves voltage regulation. By reducing the current flow, power factor correction can help to stabilize voltage levels and reduce voltage drop, ensuring more efficient operation of electrical equipment. Fourthly, it reduces equipment losses. Lower current flow translates to reduced resistive losses in conductors and equipment, prolonging equipment life and improving overall system efficiency. The selection of appropriate capacitors for power factor correction depends on several factors. Firstly, the size of the load, which is the amount of reactive power that needs to be compensated for. Secondly, the system voltage, which determines the voltage rating of the capacitors. Thirdly, the harmonic content of the system, which may require the use of harmonic filters in conjunction with the capacitors. Fourthly, the location of the capacitors. Capacitors can be installed at individual loads, at distribution panels, or at the service entrance, depending on the specific requirements of the system. Several methods can be used to determine the appropriate size and location of capacitors. Firstly, conducting a power factor study. This involves measuring the power factor at various points in the system and analyzing the data to determine the optimal capacitor size and location. Secondly, using power factor correction software. This software can simulate the effects of capacitors on the system and help to determine the most cost-effective solution. Thirdly, consulting with a qualified electrical engineer. An experienced engineer can assess the specific needs of the system and recommend the most appropriate power factor correction solution. Regular maintenance of power factor correction equipment is essential to ensure its continued performance and reliability. This includes firstly, inspecting capacitors for signs of damage or deterioration. Secondly, testing capacitors to verify their capacitance and insulation resistance. Thirdly, cleaning capacitors to remove dust and debris. Fourthly, tightening connections to prevent loose connections and overheating. Fifthly, monitoring the power factor to ensure that it remains within acceptable limits. Harmonic distortion can negatively impact electrical systems, leading to equipment malfunction, increased energy losses, and reduced system capacity. Harmonics are voltage and current waveforms that are multiples of the fundamental frequency, typically 60 Hz in North America. Harmonic distortion is caused by nonlinear loads such as electronic devices, variable frequency drives, and arc furnaces. These loads draw current in a non-sinusoidal manner, which generates harmonics. The effects of harmonic distortion can be wide-ranging. Firstly, equipment overheating. Harmonics can cause transformers, motors, and other equipment to overheat, reducing their lifespan and potentially leading to failure. Secondly, increased energy losses. Harmonics can increase the current flow in conductors, resulting in higher resistive losses and increased energy consumption. Thirdly, voltage distortion. Harmonics can distort the voltage waveform, which can cause malfunctions in sensitive electronic equipment. Fourthly, nuisance tripping. Harmonics can cause circuit breakers and fuses to trip unexpectedly, disrupting operations and potentially causing damage to equipment. Several methods can be used to mitigate harmonic distortion. Firstly, using harmonic filters. Harmonic filters are passive or active devices that are designed to block or reduce the flow of harmonic currents. Secondly, using harmonic reducing transformers. These transformers are designed to reduce the generation of harmonics by nonlinear loads. Thirdly, using line reactors. Line reactors are inductors that are installed in series with nonlinear loads to reduce the harmonic currents that they generate. Fourthly, using active harmonic conditioners. These devices actively inject current into the system to cancel out the harmonic currents generated by nonlinear loads. The selection of appropriate harmonic mitigation techniques depends on several factors. Firstly, the severity of the harmonic distortion. Secondly, the type of nonlinear loads that are generating the harmonics. Thirdly, the sensitivity of the equipment that is being affected by the harmonics. Fourthly, the cost of the mitigation techniques. Regular monitoring of harmonic distortion is essential to ensure that it remains within acceptable limits. This can be done using harmonic analyzers, which measure the voltage and current waveforms and calculate the harmonic content. If harmonic distortion is found to be excessive, appropriate mitigation techniques should be implemented to protect equipment and improve system efficiency. Electrical safety is paramount in any electrical installation or maintenance activity. Several safety precautions must be observed to prevent electrical shock, burns, and other injuries. Firstly, always de-energize circuits before working on them. Use a voltage tester to verify that the circuit is de-energized before touching any wires or components. Secondly, use lockout-tagout procedures to prevent circuits from being accidentally re-energized while work is being performed. Thirdly, wear appropriate personal protective equipment, including safety glasses, gloves, and insulated footwear. Fourthly, use insulated tools to prevent electrical shock. Fifthly, never work on electrical equipment in wet or damp conditions. Sixthly, be aware of the potential for arc flash, which is a dangerous electrical explosion that can cause severe burns and other injuries. Use appropriate arc flash protection, such as arc-rated clothing and face shields. Seventhly, follow all applicable electrical codes and standards. Eighthly, if you are not qualified to perform electrical work, hire a licensed electrician. Regular training on electrical safety is essential for all personnel who work with or around electrical equipment. This training should cover firstly the hazards of electricity. Secondly, safe work practices. Thirdly, the use of personal protective equipment. Fourthly, lockout-tagout procedures. Fifthly, arc flash protection. By following these safety precautions and providing regular training, the risk of electrical accidents can be significantly reduced. Troubleshooting electrical problems requires a systematic approach to identify the root cause of the issue and implement effective solutions. Firstly, gather information. Talk to the user of the equipment or system to gather information about the problem, such as when it started, what symptoms are being observed, and what actions have been taken so far. Secondly, inspect the equipment or system. Look for any visible signs of damage, such as broken wires, loose connections, or burned components. Thirdly, test the circuits. Use a multimeter or other test equipment to measure voltage, current, and resistance at various points in the circuit to identify any anomalies. Fourthly, analyze the data. Use the data collected to identify the most likely cause of the problem. Fifthly, implement a solution. Once the cause of the problem has been identified, implement a solution to fix it. This may involve replacing a faulty component, repairing a broken wire, or adjusting a setting. Sixthly, verify the repair. After the repair has been completed, verify that the problem has been resolved and that the equipment or system is functioning properly. Several common electrical problems and their solutions include firstly, blown fuses or tripped circuit breakers. This may be caused by an overload, a short circuit, or a ground fault. The solution is to identify and correct the cause of the overload, short circuit, or ground fault, and then replace the fuse or reset the circuit breaker. Secondly, loose connections. This can cause intermittent operation, voltage drop, and overheating. The solution is to tighten all loose connections. Thirdly, faulty components. This can cause a variety of problems depending on the component. The solution is to replace the faulty component. Fourthly, wiring errors. This can cause a variety of problems depending on the error. The solution is to correct the wiring error. By following a systematic approach and using appropriate test equipment, electrical problems can be efficiently and effectively troubleshooted.